So good morning to all of you, my students. Today I will start my lecture number 10. In today's lecture, we will discuss about some relations, and after that equivalences. We will introduce equivalence relation and related results. So we will do all these things. Let's start. All of you remember that in the last lecture we did this result. Then domain phi composition psi is equal to range phi intersection domain psi phi inverse. This we have proved. We will use this, that's why I wrote here. Now we introduce one definition, that is phi belongs to Px is called mapping. If domain of phi is equal to x. Now you see, we know all about partial maps. Partial maps, see, all binary relations are not partial maps. Those binary relations are the partial maps which have unique image, correct? For example, if the image of x is y1 as well as y2, then y1 must be equal to y2. This is about partial maps. And now what about map? One more restriction will be there, that is every element is related to unique element in codomain. That is why the domain of phi is whole x, correct? Domain of phi is whole x. It means what? It means there is no element is remaining which is not related to codomain. So that is called a mapping. So all of you can see that it is denoted by tau x. Tau x is what? Tau x is denoted from, that is phi from phi is a subset of x cross x such that phi is a map like this, isn't it? I mean, it's such a binary relation such that phi is a map. Or you can say phi is a map from x to x. Phi is a map. So its collection of all maps is denoted by tau x. After that, px, that is phi subset of x cross x such that phi is partial map here. Phi is map, that is what? That is domain of phi is what? Whole x. And here what? Phi is partial maps, that is what? That is you say that x phi will be 1. Number of elements in x phi, if you say that it is 1, the unique image, x has unique image, it means that is, or you elaborate, it means that x comma y1, x comma y2 belongs to phi implies what? Y1 is equal to y2. And what is this? This is the set of all binary relation, that is a collection of all binary relation. Collection of all binary maps. Phi is binary relation on set x. If you collect all binary relation, so what is the relation in between all these? You see that tau x is contained in px and it is contained in bx. Now if we define same composition as a binary operation, so we have already seen that set of all partial maps is a subsemigroup of set of all binary relation. Here it is a subsemigroup. Yeah, well, you can see here that this is also a subsemigroup of this, and also you see that it is also a subsemigroup. Means tau x is a subsemigroup of px, tau x is a subsemigroup of bx. Correct? But we have to prove that. You see that tau x being a subset of either px or bx, all elements of tau x will follow associative law. Correct? Being a subset of px as well as bx, it follows associativity. What we have to prove? We have to prove closure law. That if you take any two elements from tau x, you have to prove their composition again belongs to tau x. Correct? So you see, if you take any phi comma psi belongs to tau x. Correct? Then what is our claim? Claim is that in order to show that phi composition psi belongs to tau x, what we have to show, that is domain of phi composition psi is what? X. See, what is the definition? Definition is what? Phi belongs to px is called mapping if domain of phi is what? X. This is the definition. Correct? So if we have to prove, what is our question? This is the proposition. Yeah, well, so our proposition, I think it is 4.8, that is tau x is subsemigroup of bx. In the place of bx, it can be px also. Tau x is subsemigroup of px as well as bx both. Anyway, so basically what we have to prove domain of in order to prove phi composition psi is map, we have to prove that domain of phi composition psi is what? X. So we have already proved this theorem. Correct? That is domain of phi composition psi is equal to range phi intersection domain psi. Basically put you here as like this. First use this. So basically you have taken an element tau phi comma psi belongs to tau x, well tau x is contained in px as well as. So phi and psi both goes in px. When phi and psi both goes in px, then already we have proved that domain of phi composition psi is what? Range phi intersection of domain psi and intersection of into phi inverse. Now what is the value of domain psi? Value of domain psi is what? Range phi intersection x phi inverse. Why? You can give the logic since psi belongs to since psi is a map. As we have taken phi psi both from tau x, so psi is a map when psi is a map, it means what? Domain psi is what? X. So range phi intersection X. X is the largest set. Range phi is the subset of X. So what will be here? It is what? Range phi into phi inverse. Range phi means there is X phi, phi inverse. So it is what? Phi inverse will cancel out. So what will be the result? X. So domain phi composition psi is equal to X. It implies what? Phi composition psi goes in tau X. So we have proved that tau X is closed with respect to this composition. Is it clear? So first you have to prove this thing. If phi comma psi belongs to Px, as we have already proved this, so you have to prove first, that is domain of phi composition psi is range phi intersection domain psi bracket close into phi inverse. First you have to prove this. After proving this, you will do all these things. Then phi composition psi goes in tau X, and tau X being a subset of Px. Px is a subsemigroup, isn't it? Px is a semigroup. Px is a semigroup. All elements of Px will follow associativity, and all elements, since the member of tau X are the member of Px, so it will definitely follow again associativity. Correct? So in this way, phi composition psi goes in tau X as well as, so hence tau X is subsemigroup of Bx. Oh, sorry, Px. Just I am writing. Being subset of Px follows associativity. Hence, S subsemigroup of Px. Isn't it? So what happens? Tau X, we have shown that it is what? Subsemigroup of Px, and Px. So well, we have shown that tau X is basically a semigroup. Correct? Tau X is a semigroup, and also tau X is a subset of Bx. Is it clear? Tau X is semigroup with respect to the composition, and also it is subset of Vx. It means what? We can also write, so tau X is also subsemigroup of Bx. Basically, as we know well, what is the definition of subsemigroup? See, if you have to prove T is a subsemigroup of S, then if T is a subset of S, and you have to prove T is a subsemigroup of S, what you have to prove? What is your claim? That is, AB belongs to T for every AB belongs to T. If you are able to show, then you are done. So we have done. Tau X is a subset of Bx, as well as tau X is a semigroup. Isn't it? It is closed. AB belongs to T for every AB belongs to T. Then tau X is also a subsemigroup of Bx. So in this way, this is the relation between tau X, Px as well as Bx. Correct? So Now we move to another result. If phi belongs to Px, then phi inverse belongs to Px if and only if phi is 1, 1. So see what is given here. Phi belongs to Px, then phi inverse belongs to Px if and only if phi is 1, 1. So let's start. Let you assume that phi inverse belongs to Px. Correct? And what is our claim? We have to show that phi is 1, 1. For this, let y1 phi is equal to y2 phi, where you y1 and y2 belongs to x. Remember, in this book follows such that the elements are taken on the left side. It's a matter of writing. Both are correct. So y1 phi is equal to y2 phi. Correct. So in order to prove phi is 1, 1, what we have to prove? We have to prove that y1 is equal to y2. Correct. So this is the y1 phi is equal to y2 phi, and we have to prove y1 equal to y2. We can assume without loss, we can assume here x, say both are equal to some like this. Then what happens? Then it means what? Then y1 comma x and y2 comma x belongs to phi. Correct? Because image of y1 is x, image of y2 is x, it means that both have same images. It implies that x comma y1, x comma y2 belongs to converse of phi. It is converse of phi. So x comma y1, x comma y2 belongs to phi inverse. So it implies that since phi inverse belongs to Px, it means that y1 must be equal to y2. It implies y1 is equal to y2 since phi inverse belongs to Px. So it implies that phi is 1, 1. Now we do converse. Conversely, let phi is 1, 1. Let x comma y1, x comma y2 belongs to phi inverse. Then y1 comma x and y2 comma x belongs to phi. If converse of phi, so it belongs to phi here. Correct? So now from here, what we can write? We can write that y1 phi is equal to y2 phi is equal to, from here it is clear this. See, y1 phi is what? X, and y2 phi is what? X. Image of y1 is x, image of y2 is x. So y1 phi is equal to y2 phi, and it implies y1 equal to y2 since phi is what? 1 1. So it implies that phi inverse goes in Px, correct? So in this way we have proved. So anywhere have we used phi belongs to Px the information, because it is given that if phi belongs to Px, then phi inverse belongs to Px implies phi is 1 1. So have we used this or not? Let phi inverse belongs to Px. It means we have to show that this is 1 1. Y1 phi is equal to y2 phi. It means that is equal to x. So y1 comma x and y1 comma x and y2 comma x both belongs to phi. So x comma y1 x comma y2 belongs to phi inverse. It implies that y1 equal to y2. Okay. Okay. So y1 equal to y2. So it implies phi is 1. Okay, well, this is the first part basically. This is the first part. We have not used phi belongs to Px in this part. In the second part, hopefully we will be using this. Second part is that